Bismillahirrahmanirrahim. Now our next theorem that let T be a linear transformation from the vector space U to the vector space V over the same field F, then the range set or image set in V under the linear transformation T consists those vector V of the vector space V over the field F such that these vector V are the images of of a vector u of the vector space u over the same field F. Is this subset V, this subset of the vector space V is a subspace of the vector space V. Proof. Since for an element 0, additive identity element 0 is an additive identity element of the vector space V, then by a previous theorem only the 0 vector under the linear transformation T map to the 0 vector of the vector space V over the field F, that is this resultant element which is the image of the element 0 of the vector space U, vector space U over the field F is contained in the range set of the vector space, range set of the linear transformation T. That is the range set of the linear transformation T is non-empty. Now for any two element V1, V2 in the linear in the range set of the linear transformation T, there exists two vector U1, U2 in the vector space U such that V1 is the image of an element U1 under the linear transformation T of the vector U, and V2 is the image of a vector U2 of the vector space U over the field F under the linear transformation T. And for any two scalar a b in the field a u1 plus b u2, the linear combination of v1 and v2 is equal to a v1 is equal to t u1 comma b v2 is equal to t u2, and by the condition or by definition of the linear transformation, this step can also be written in the form of t a u1 comma b u2. Also by the vectors, also by the definition of the vector space, that the set U over the field F is a vector space over the field F. Therefore, for any two element U1 and U2 in the vector space U and AB are the element of the field, the linear combination A U1 comma B U2 is again an element of the vector space U. Therefore, this resultant element is an element of the vector space U, and T is a linear transformation, that is T is a mapping. So each element of the vector space U is an image of is a free image of the element of the vector space V. That is T a u1 comma b u2 is again an element of the range of T. That is this is the free image of an element of the vector space V. That is V. That is there exists an element V1, suppose that is there exists an element V dash in the vector space V such that T a u1 comma b u2 is equal to V dash, where V dash is an element of the vector space V. And this resultant element is the image of this element which is under the linear transformation T. Therefore, this element V dash is contained in the range of the linear transformation T. That is the V dash is equal to T a u1 comma b u2, which is an element of the range of the linear transformation T. But T a u1 comma b u2 is equal to a v1 comma b v2 according to this condition. That is, this element is an element of the range of T. Hence, for any two element v1 v2 in the range of T and any two scalars AB such that A v1 comma B v2 is contained in the range of T. Therefore, the range of T satisfy the condition of the vector space over the field F, but the range of T is a subset of the vector space V, and hence we can decide that the range set for the linear transformation T is a subspace of the vector space V over the field F.